Welcome to The Explainer. Today, we're going to tackle a topic that sounds kind of scary, but is basically a superpower for any programmer. We're talking about time complexity. We're going to break it all down so you can look at code and know almost instantly how good it is.
All right, let's just dive right in with a situation every single programmer has faced. You've got two pieces of code, right? They both spit out the correct answer. So which one's actually better? How do you even decide that?
This isn't just some textbook question. In the real world, we want our apps to be fast, to be responsive. Picking the right code is what separates a great user experience from a clunky, frustrating one.
To really compare them, we can't just go with our gut. We need a solid, reliable standard, a universal yardstick that works no matter what computer you're on or what else is running.
So, before we get to the right way, let's talk about the wrong ways. These are the traps pretty much everyone falls into at first when they try to measure their code.
So our first instincts here are usually, wrong. You might think, I'll just time it with a stopwatch. But think about it. My super fast machine is going to get a totally different time than an old laptop. What if you've got a bunch of stuff running in the background? The numbers are all over the place, completely useless. Okay, what about just counting the lines of code? Even worse. You could have one tiny loop that runs 1,000,000 times and then 100 lines of code that only run once. The line count tells you absolutely nothing about the actual work being done. We need something way smarter.
And that's where this idea of time complexity comes in. This is the real deal. It's the industry standard for how pros actually judge and compare algorithms.
Okay, this is the most important part to get. We're not measuring time in seconds or milliseconds. Time complexity couldn't care less about that. What it cares about is growth. It's all about how the runtime scales. If I double the amount of data I give my code, does the work double? Or does it, quadruple? Or worse? That's the question we're trying to answer.
And the key to unlocking all this is a simple idea called dominating terms. It's really just about learning to focus on what truly matters and just ignoring all the noise. Let's make this super simple with an analogy. Just imagine for a second you go out and you buy two things, a brand new car and a simple little bicycle.
So your friend calls, all excited, and asks, "Hey, what'd you buy? What are you going to say? What's the headline news from your shopping trip?"
You're going to say, "I just bought a car," right? Of course. Nobody's going to say, "Well, I bought a car and a bicycle." The cost of the bicycle is just a rounding error compared to the car. It's basically irrelevant. You focus on the big, expensive, dominating item.
And that right there is the whole idea behind time complexity. It's exactly the same thing. When you look at your code, you're looking for the car, that one part that does the most work, the part that's going to slow things down as your input gets bigger. And you learn to just ignore the bicycles. All those little quick operations, they just don't matter in the grand scheme of things.
Okay, so how do we actually find these cars in our code? Well, the good news is there are a few really common patterns that you can learn to spot.
First up, the absolute fastest you can get. It's called constant time, or big O of 1. This is for code that takes the same amount of time no matter what. Whether you give it one thing or a billion things, it's just as fast. Think simple math or assigning a variable. It just runs. It doesn't grow.
Next up is probably the most common one you'll see, linear time, or big O of n. This is where the runtime grows in a nice, predictable, straight line with your input. Got a single loop going through a list of n items? That's probably O of n. Double the items, and you pretty much double the time. Makes sense.
Now here's where things start to get slow. Really slow. Quadratic time, or big O of n squared. This should be a big red flag for you. It almost always happens when you've got a loop inside of another loop. For every item, you're looping through all the items again. This thing gets out of hand really, really fast. And on the flip side, we've got one of the best you can hope for, logarithmic time, or big O of log n. This code is incredibly efficient. Why? Because with every single step, it cuts the problem down, usually in half. So even with massive inputs, the amount of work it has to do grows incredibly slowly. It's fantastic.
Okay, we've got the rules, we know the patterns. Let's put this into practice and analyze some actual code.
Take a look at this. It might look a little complicated, but don't worry. We've got this. It's actually just a mix of everything we've just talked about. Let's go through it line by line.
So that first little bit, just setting a variable and printing it, that runs once. It's O of 1, a bicycle. Then we've got that single for loop. It runs n times. That's our classic O of n. Then, the nested loops, a loop inside a loop. That's our big, slow car, O of n squared. And finally, that while loop that keeps cutting n in half, that's our super efficient O of log n. So now we've got all four in our code. We've got O of 1, O of n squared, and O of log n. But just remember the car and the bicycle. We only really care about the one that's going to cause the biggest traffic jam, the one that grows the fastest.
And when you look at how these grow, it's not even a contest. As n gets bigger, that O of n squared part just completely takes over. It makes everything else look tiny and insignificant, like a bunch of bicycles next to a monster truck.
So, for that reason, the overall time complexity of this whole block of code is just big O of n squared. That's it. We find the biggest, baddest part and ignore all the rest. And just like that, you've analyzed the code and found its weak spot.
And really, that's the whole game. Once you can spot these patterns, you gain this incredible ability to instantly judge your code's efficiency. Thanks so much for joining this explainer.